Okay.
Okay, so our third speaker today is Isaac Vliem from Bethel. Please go ahead.
Yep. All right. Can everyone see this?
Yes.
Okay. So sorry about that, everyone. Computer died randomly, Murphy's Law and such. So this past summer, I had the opportunity to work through an internship that was provided by NASA Langley Research Center on a team. And the team project at the end, we decided would be named the Terrestrial Unmanned Roving Vertical Takeoff and Landing Rover, or TERVTOL. And so I'm going to tell you a little bit about that. So before we really get into the nitty-gritty, I wanted to go over some important details, primarily the team structure. There were 4 subgroups on the making up the major team. The aeronautical subgroup, which was tasked with designing the flight systems of the vehicle. The mechanical subgroup, which was tasked with designing ground travel systems. And they spent a lot of time focusing on the chassis design as well. And both the aeronautical and mechanical worked together quite a bit to design a chassis and other shared components of the vehicle. The software subgroup was tasked with designing the program hierarchy and the logic of the rover to make it autonomous and as intelligent as possible. The navigation subgroup was tasked with designing the navigational algorithm, try to make it robust and efficient. And then both were tasked with integrating that navigation program into the decision-making of the rover itself. So over the course of the summer, we went through a design process, which is kind of listed below. So at the very beginning, we defined our mission and the major objectives we wanted to accomplish during the internship. And then we broke off into the 4 separate subgroups to continue designing objectives and requirements that each specific subgroup would then use to track their progress. We performed trade studies when we were in the subgroups, trying to figure out what was already out there in terms of literature or work that's already been done, and to see where we would need to come up with our own methodology for this project. And then finally, the subgroups moved into the designing and the testing and the redesign phase, wherein the subgroups began to work together more because we were all working on the same vehicle. And so we saw a lot of cross play between the different subgroups and the work they were doing. And then finally, we came up with our first iteration model at the end of the summer. So mission definition. That was a major part of our project because when we got the internship from the center, we were given a very incomplete mission requirement in terms of we would need to fill in the details. We were given, you basically need to design a multimodal vehicle that can operate autonomously without GPS control. It's pretty much all we were given. And so we had to take that and run with it. And so we met as a large group and came up with some main criteria, which we decided would help us to navigate where we wanted to take this project. So some of the important aspects were we wanted this project to be scientifically important. It's all well and good to design an interesting vehicle, but we wanted it to be able to do something. So we wanted it to be able to go to a place that was scientifically important, relevant, and to perform potentially tests. Another major criteria was that there was not, we didn't want any satellite coverage or GPS availability. Now this is very difficult to find in this modern day. However, because we were going to be programming a robot that was not supposed to be using that kind of thing, that was not a factor we were going to consider. Some extreme temperature variability would be nice because it would make the project a little bit more interesting in terms of you have to insulate things properly. And then a high number of obstacles is also important because that's how we would be testing how our rover would react to in terms of driving versus flying. And so out of those criteria, we kind of picked a few different areas, including the Grand Canyon, an Arctic climate, a flood zone, a disaster zone, among others. And our final choice ended up being the Arctic. And so our mission profile we came up with was about a 15-day mission in the McMurdo Dry Valleys in Antarctica, 135 kilometers total with 1,750 meter total altitude change. As you can see on the chart below, it shows us where the driving would take place, the solar recharging would take place, and then finally where we would have to fly, testing that multimodal capability. So after we came up with the mission profile, we had to come up with some design requirements which would help us kind of figure out where we wanted to take this project. So below are a number of the overall requirements that we came up as a main team. Like I mentioned before, each subgroup kind of broke up and came up with their own design requirements. But some of the main ones that we wanted to consider was that the system shall operate autonomously and efficiently, maneuvering over extreme terrain. This was part of the multimodal aspect of this project. We wanted a rover which would be able to move around over hazardous terrain that traditional rovers might not be able to. Another major requirement that we wanted to hit was the system that will be able to operate on a renewable energy source. Obviously, if you run out of power in the middle of nowhere, you can't just wait for a battery change. And so we wanted our rover to be able to operate off of solar energy. And then one of the last major ones that I want to touch on briefly is the system should have the land traversing and flight capabilities. This was one of the major aspects that we were given by our principal investigator. And so we needed to make sure we integrated this in the best way possible. And it was quite a challenge, but also very fulfilling to try to do this. So now I'm going to give a brief overview of each of the different subgroups and what we were working on before going into more detail. So the primary goals of the aero and mechanical subteams were to develop the multimodal vehicle, like I mentioned. This vehicle was supposed to be able to traverse various terrains by ground or air, depending on the computer algorithm's decision. We also wanted to incorporate about a 4-kilogram payload capacity for scientific purposes, whether that be sampling or collecting interesting artifacts for later analysis. We wanted to be able to incorporate some kind of ability to take things from a specific place and then analyze them later. Another aspect that we wanted to consider was the long-term survivability of the project. You can't just call AAA if the rover breaks down in the middle of nowhere. You have to design it in such a way that you won't have to worry about it breaking down. You want to try to minimize the number of ways it could fail. And like I mentioned earlier, to implement a renewable energy source, that was a big aspect of this as well. And now onto the software navigation overview. I was part of the software navigation subteam, so this is a little bit more familiar to me. So the primary goals of these two subteams was to outline the software and to design a finite state machine for the logic controlling. This took quite a long time. We spent about a month working on the initial software diagrams in the finite state machine because it was just that important. We needed to nail that down. We wanted to be able to map and localize the vehicle without the use of GPS. This was an interesting challenge to overcome. Because since we weren't able to use GPS data, we had to rely on onboard sensors. And for those of you who have worked with robotics in the past, getting those to work together can be challenging, especially when we're not dealing with actual physical hardware. And then another major goal was to be able to determine the occupied space that the rover took up from a generated map. This was part of the autonomous navigation that we were supposed to be working with. We wanted to be able to generate a map of the 3-dimensional terrain around the rover and then be able to localize that rover using onboard sensors so that the rover could then path plan accurately and efficiently. Another major goal was to design a heuristic path planning algorithm for the multimodal vehicle. And then finally, to simulate the vehicle and the algorithms. This, due to COVID, we weren't able to be in person for most of the summer. And so a lot of what we focused on was simulation. So now kind of moving into more of the specifics, the design and testing phase for each of the subgroups. Aeromechanical worked very heavily with 3D modeling. like I mentioned before, since the internship was mostly virtual, we relied on a lot of 3D modeling to come up with concepts. So for example, the integrated wheel and prop designs, that was an interesting challenge because we had to design it from the ground up because of the multimodal capabilities that the rover was supposed to have. And so as you can see kind of down here in the middle, this was the final wheel design that we came up with for the first iteration. It integrates 2 propellers within each wheel. There are 4 wheels, so 8 propellers total. And another aspect that we had to consider was the chassis. We had to make this as light as possible, but also as strong as possible to be able to absorb impacts and to keep the rover from breaking apart. And so here's a little model of the chassis down here. The drivetrain was also an interesting challenge. I was not particularly involved in this, but I was told that there was a lot of effort that went into developing this drivetrain to make it as powerful as possible. And then electronic component mounts for the camera systems, the gyroscope, the computer were all laid out in 3D modeling as well. Computer analysis was a major part of this. Also, the stress and survivability tests that went into this were extensive. As you can see here, there's an image down here of the chassis stress test that the aeromechanical teams worked on. And then we were also able to work on physical propeller testing. Last 4 weeks of the internship, we were able to work in person from a hotel. And so we were able to get together and start putting some of this practically into hardware. There's a custom design right here and here that kind of demonstrate the ingenuity of the people behind it. It was really helpful to be able to do these propeller tests to kind of get a baseline of what we were working with. But towards the end of the summer, the aeromechanical sub-teams worked with a company called Vliem, which did some large-scale propeller testing for us. And then finally, with the simulated nature, we worked with X-Plane, which is a flight simulator, to kind of test vehicle responses. Now into the software navigation side of things, we worked a lot with command hierarchy design. Towards the beginning of the summer, we worked with the inner and outer loop control, designing that how the path planning node would talk to the drive and the flight nodes and how those would interact with the servo motors and with the flight controller. We also worked with something called Robot Operating System, or ROS, which is like a large open source library for robotic control. We developed a ROS node flow diagram, which helped us to understand where topics were being published to and where information was going. And then we spent a lot of time on the finite state machine, which was essentially the command hierarchy of the rover deciding when things would happen due to what stimuli. Visual odometry was a major part of this project as well. Since there was no GPS availability, we had to essentially use a camera to take in the surrounding environment and then process that. So we used an algorithm called VINS Fusion, which was developed by Hong Kong University, which essentially takes 3D environment scans from a camera and converts that into a point cloud. We also, for mapping purposes, use a program called Octomap, which takes point cloud data and transforms it into a 3-dimensional digital environment. And so the navigational hierarchy that we designed essentially took camera images, used VINS Fusion and converted those images into point cloud data, and then converted the point cloud data into Octomap environments. And then those Octomap environments would be used to be sent to the controller, which would then decide where the rover was going to go next. So up here, you can see that in this gazebo simulation, the rover is driving around, and here's the camera view, and on the bottom is an Octomap generated environment based on that camera data. So at the end of the summer, we came up with our first iteration model. This is PureVTOL in all its glory down here at the bottom, a 3D generated model of it. And above are some exploded diagram views of it. And to the right here are some images taken from the computer simulation model that the software navigation teams worked on, testing the capability of the rover to switch between driving and flight modes, and then to also follow some waypoints that we programmed for it. To end this talk, I want to comment a little bit on working virtually and how that worked. Because we were working virtually, we were not able to make a prototype for this project, which was a little disappointing. So simulations then became our primary focus. Being able to simulate the model in a three-dimensional environment was very critical for testing our navigational algorithm and how that worked. And then there were also some challenges that needed to be overcome.
Sorry to bug you, Isaac, just giving you a 1-minute warning.
Yeah, thanks. There were also some challenges that needed to be overcome, including team bonding, making group decisions, outlining and designing without whiteboards, and staying updated on team progress. These aren't necessarily things that you might think about when you need to work virtually, but they are considerations that you need to take into account. Fortunately, given enough time, we were able to overcome these challenges. So in conclusion, I'd like to thank the Minnesota Space Grant Consortium for funding my stipend for this project. It was very good in terms of a learning experience for me. But I'd also like to thank NASA Langley Research Center for providing the internship experience and the PI for the project, Dr. Elizabeth Ward. Questions?
Thank you, Isaac. So we have a minute or two for maybe 1 or 2 questions.
Are there plans to build this prototype?
Right. So this past fall, we actually did a continuation on this internship where the software and navigation subteams continue to develop the computer programming. And there have been talks about potentially building this project as a side thing this next summer. And not necessarily all the team would be involved in that, but those who would try to build an actual physical model of the system. Yeah.
I have a question.
Mm-hmm.
So I'm curious to know how I can be involved with this project. It sounds really interesting. I'm not sure where to kind of like start because I'm a freshman and I want to pursue computer engineering.
Yeah. So each year, NASA Langley has what they call the NASA Academy. And this is essentially what led to this internship experience. Each year, the subject is different. I don't know what this year's project is working on, but here's the website for the Academy. There are some factors that they take into account when choosing applicants, and like standing in classes, GPA, stuff like that. I know that we did actually have a freshman on our team over the summer. So there is definitely ways to get involved in that way.
And the person that asked the question, I'm not sure, I can't see who you are, but there are more opportunities, not only at NASA, but other places as well. So drop me a note or contact us and we could probably point you in the right direction.
So it turns out we actually, one of your advisors was Ryan Bowers, who was from Minnesota Space Grant previously as an Academy participant. And we just landed another Academy participant at Langley for this coming summer. They're studying wildfires.
Oh, okay.
So yes, NASA Academy at Langley has been good to us.
Yes, it's a really good experience.
So thank you so much,
All right.
Isaac. I think perhaps we should go on. Is that all right, Demos?
Yep, we should. Thank you very much. Great talk.